In this video, we're going to discuss basic optics for mirrors and lenses, and there's two equations we should know. And in addition to knowing these equations, it's probably more important to understand sign conventions, because you can have the values, but if you have this wrong sign conventions, you'll get the wrong answer. And it's also important to have an understanding of what goes on, so when I get an answer, I see, does that make physical reality sense of what I expect, and there I can check myself. So the first equation, that's the kind of a general equation for all mirrors and lenses, is 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. And I can solve for distance of image and do some algebra, and here's two alternative forms for solving for distance of image as a function of focal length and distance to the object, and those help me understand kind of what's going on as well. The second equation is magnification, and magnification, shown by lowercase m, is a ratio. It's a ratio of the height of the object I would see if I didn't look through a device like a lens or a mirror compared to the height that I see when I look through this device. And if when I look through one of these devices the image appears greater than I would see if I didn't look through one of these devices, then there has a magnification factor which has an absolute value greater than 1. If the image is smaller, looking through one of these devices, then the height of the object that I would see without looking through them, then the magnification factor would have absolute value less than 1. If the object is in reality upright, so if you get your feet on the bottom and your head on top, and the image, it maintains that certain orientation, the feet are on the bottom, the head is still on the top, then this would be a positive. If it's inverted, and now it's looking through the image, your feet are on the top and your head's on the bottom, then this would be a negative. And there's a relationship, so this is the common way you would think about magnification. Now through one of these devices, there's also a relationship between where the distance of the object is and the distance where the image appears. And there's, if the image is being magnified, it appears like it's a long way away from this, it's very large, it's very high height, then in reality it appears as though it's a long way away from the device. And so the distance of the image is greater than the distance to the object. And when we do this relationship, when we use distance, we must remember that there's a negative sign that goes along with this. So magnification is height of the image over the height of the object, or minus the distance of the image to the distance to the object. And we kind of have 4 cases we're going to look at. We're going to just divide it into 2 right here. So the first one we're going to look at, the first grouping are where this focal length is defined negative. And where focal length is defined negative, that's for 2 cases, a convex mirror and a divergent lens. When I have a concave mirror or a convergent lens, then I'll have focal lengths greater than 0. And that's a little more complex as far as how the resulting image height and the image distance and the magnification result. And so we'll talk about that later, but we'll cover the first case, much more easier case here, where focal length is less than 0. And we'll talk about convex mirror, and then we'll talk about divergent lens, and it turns out that it's actually kind of a very, very similar form for how everything solves out. For convex mirror, what helps me to think about is a real case where I know a convex mirror, and the one we're most familiar with, at least adults, is when I'm driving a car, I look in the rearview mirror of the car, it's a convex mirror I'm seeing, and the statement that's on there, which is the warning statement, helps remember what happens. And it says, objects in this rearview convex mirror are closer than they appear. So how does it help remember it? Well, appearance is kind of what the image is. So I see an image in that mirror, and it's saying the objects are really closer than they appear in that image. So that's telling me that the image is much smaller than the real that object would otherwise appear. So I look through that mirror, that convex mirror, and I look and I see an image. For example, I see a car, and that image height is a certain height. Where if I just turned around, if that car is the same distance away from me, I just turn around and look at it, I would see the height not looking through that mirror. I'd be the same distance away from that car, but I'd turn around and look at it, and that object would seem bigger. And so therefore, this is kind of telling me I know that my magnification has an absolute value less than or equal to 1. The other thing it also tells me when I think about this statement in the convex mirror is when I look at a car through my rear mirror, the car never seems inverted. It never looks. I don't see the tires on the top and the top of the car on the bottom. So therefore, the image is always upright. So therefore, I know this magnification factor has a value that's non-negative. Let's say it could be 0 when the image is at infinity, but it's at least this is non-negative. So this statement kind of helps me understand right away. If I know it's a convex mirror or a divergent lens, something has a negative focal length, I right away know that my magnification factor is less than or equal to 1, and it will approach 0 as the object is at infinity away. So that helps me kind of understand what's going on there. Now let's kind of talk about distances, because distances and sign conventions are very important. For a mirror, the surface of the mirror is defined as the distance 0. For a lens, the center of the lens is the 0 point. And let's say this is the reflective side of the convex mirror. So here's the object on this side. The distance to the object is always a non-negative number. So this is the object in distance in front of this convex mirror. And for a mirror, if the image is also defined as positively in this direction, because if I saw an image which was real, I would expect, since a mirror is a reflective device, I would expect that a real image would appear also on this positive side. So on this side of a mirror, on this reflective side where the object, that's defined to be a positive distance, both for the object and for the image. Now that's different. We have different expectations for a lens. The center of the lens is the center line, and the distance going from the center of the lens to the object is defined positively here. So the object is defined on one side of this lens, and if I have a real image which appeared, since a lens works by refraction, I would expect the image to appear on the opposite side of the object for a lens. On the same side, so of a mirror, on the opposite side, the image would appear than the object in a lens. So therefore, for a lens, regardless with divergent or convergent, I define a positive image distance as the distance on the opposite side of the lens from the object. And this is part of the reasoning why sign conventions are so important with lenses and mirrors, to know what's defined as 0 and what's defined as positive, both for the distance of the object and for the distance of the image, because it's different for mirrors and lenses. So now let's think about what happens with this mirror. And we'll think about, so there's my surface of the mirror, here's a reflective side, so here's the object looking, me looking into this mirror, and we'll start out thinking about what happens when this object is right up against the mirror. So the distance of the object is 0. So if the distance of the object is 0, it turns out if I solve these equations, it'll be solve this equation, the distance of the image will also be 0. And the height of the object and the height of the image will be 1, so therefore the magnification factor will be 1. And then as I start to move the object away from the surface of the mirror, so I'm making my distance to the object going from 0 to something greater value than 0, what I see is, as I'm going farther and farther away, it appears as though the height of the image is getting smaller and smaller and smaller, until ultimately I put the object at infinity, and then the height of the image appears approaches 0. And that image distance, where that image appears to be, from where I am, where that image appears to be, it turns out to be never positive. That image never appears to be on this reflective side. So it can be 0, but it's always going to be, it's always then it's going negative. So it's always on this wrong side that I expect to be. And also, as I expect with the convex mirror, when I look at it, the image is always upright. So I never see that car inverted. And it turns out the image is always virtual. It's never real. If I couldn't put a sheet of paper at this point back behind the convex mirror and actually see that image. So it's a virtual image. And it turns out that any time I have an image which is upright, the same direction as that, the image will always be virtual. And the distance to the image will be so those kind of things always help me remember that if the image is upright, I know it's virtual, it's not real. And then another kind of thing is think about this distance to the image, the relationship to the height. That this image is always going to appear between the back surface, between 0 and the back side of the mirror, and approaches the focal length. That distance of the image will never be outside this. Will be negative value because the focal length is minus, but I'll never see a distance of the image which is more negative than the focal length. So so this image distance and that height are always looking like this. So it's a linear relationship. Now for a divergent lens, which also has a focal length less than 0, it's going to have basically the same results as this. The only difference is distance image is measured positively on this side. So if I have an object right up against, now the 0 for a lens is the center of the lens. If the object right up against the center of the lens, the image will also appear right on that center at distance of 0, and the height of the image will be the exact same height as the true height of the object. And as I start moving the object farther and farther away from this center line of this lens, the image will start getting smaller and smaller. So the magnification drops from 1 and it starts to approach 0, and it gets to 0 when my object's at infinity. And so therefore I know my distance image is always minus, and it's always has a value between 0 and this minus focal length. And the height of, and if my image is appearing halfway between those two, then I know my image is appearing halfway between those, then I know my height is half the height, because it has a certain linear relationship. So again, for all these cases, focal length less than 0, my image, distance of the image is never positive, because it's always on the wrong side. Again, here, the image is always going to be upright, and therefore the image is always virtual. It's not a real image. So kind of knowing this limitations on D image being between 0 and this minus focal length, and then in the image and this magnification factor always being less than or equal to 1 and approaching 0 as this object's at infinity. Again, rays are going to be parallel to each other coming in here, and then they would appear to be redirected to the focal point, which is at a focal length being a minus value away from the surface of the device, the surface of the mirror or the center line of the lens. And so if I plot distance of the object to the focal length, now that's going to be a minus value for these cases, because the focal length is minus and the distance of the object is non-negative, versus magnification factor. This also helps us remember to understand things. So if the object distance is right against the mirror, or if you consider that the focal length is infinity. So if the focal length is infinity, like a plane mirror, we know that the magnification factor is 1. I look in a plane mirror, which has an infinite focal length, and therefore this number goes to 0. I see myself in the mirror the same height that I truly am. I'm a magnification factor of 1. But as I move farther and farther away, the object, the height of the image over the height of the object, the magnification is getting smaller and smaller and smaller, and ultimately when I go to infinity, as far as my object over my focal length, my magnification approaches 0. And this is taking this relationship and that relationship. Here's an equation that relates magnification as a function of distance of the object over the focal length. And kind of it turns out that if I'm at if my object is one focal length away from my surface of the mirror, or one focal length away from the center line of the lens, the magnification is a half. So the image appears half as big as it is. If I go 2 times away, it's 1/3, and if I go 10 times away, it's 1/11. And if I'm if I'm 10, if this is 10, and this is 10, and that's -1, so I'm 10 times more than my focal length. So this would be 1 minus a minus 10, which is 1/11. That my magnification factor is 1/11. So they kind of have this relationship. So no matter where I put my object, my magnification is always less than or equal to 1 for any case with a divergent lens or a convex mirror. I redrew this magnification graph. Here's what we just saw before when I had a focal length less than 0. Now I'll consider the cases over here, and this is slightly more complex where the focal length is greater than 0, and that occurs either for a concave mirror or a convergent lens. Remember, this was for a convex mirror or a divergent lens. So remember, sign convention is very important. So here focal length is defined greater than 0. And we'll start talking about a convergent lens. And what does that mean for focal length greater than 0? So for a convergent lens, for example, if I had incoming rays perpendicular to the center line of this lens, so they're, for example, coming to infinity, they would converge, actually physically converge to a point on the other side called the focal point, which is a focal length, which is a positive distance from it. And if I had rays from this side, they would converge at a focal point, which would be the exact same focal length as that focal length. And actually that turns out to be independent of the curvature of these lenses. For example, I had a curve on this one and a flat on this side. Whatever that focal length is on this side, I'd have the exact, from the distance from the center lens, I'd have the exact same focal length on this side. And I had, for example, a spherical curvature, and here's the radius of curvature. It turns out that the focal length is half of this radius of curvature. Also kind of shown right here, which is also true for for a concave mirror. That if I have a radius of curvature and my height is small compared to this radius, that I will have everything convert, all the rays, parallel rays approaching this will appear to will be reflected off this and go to this focal point, which is half the radius of curvature. And that's only true for if I have a spherical surface where the height is short, but it's generally true if I had some other shape like parabolic here, then regardless of where the height is, where these rays come in, they converge or they come towards this focal point. So now let's talk about what happens with magnification as distances change. So once again, for a lens, if I have an object, the distance of the object can be greater than or equal to 0, and if it's at the center line, the distance of the object is 0, and then I'll have, this is my distance of the object. If lenses work on refraction, so if I really would expect, if I have an image on this side, I would have an object on the opposite side. So this would be the positive distance of the image. For a mirror, works on reflection. If this is my positive object distance, this is my positive image distance, because that's what I expect to see, because if I have a real image, it'll be on that same side. So now for this, back to this lens, if I have an object which is right on the center, so for the distance of the object is 0, so the ratio of the distance of the object to the focal length is also 0. It turns out that the image will also appear at 0, and it will be, there's the magnification factor will be 1. The height of the image will be the same as the height of the object. So I'm just as I described before, the magnification is 1. Same thing for the concave mirror. If my object is on the surface of the mirror, my image will appear on the surface of the mirror, and the magnification will be 1. And that's another example of that is a plane mirror where the focal length is infinity, and then it's essentially regardless of the object distance away, as long as it's less than infinity, this ratio of some number to over infinity is 0, and is 0. So right on this axis, and my magnification factor for a plane mirror is 1. So that's a very familiar case. All 4 of the cases: convergent, concave mirror, convex mirror, convergent lens, divergent lens. If I'm right up against it, and I have a magnification factor of 1, and also true, which is also true for any plane mirror. So it's a very common scenario. So now let's consider on this convergent lens, if I start to move my object slowly away from the center of the lens, what would happen? Where do I see that image, and what's its height? Well, what I start to see is that image start to get much bigger, and it's starting to move at this absolute value. It's in the negative direction, because the D image is defined positive this way. So the D image is going negatively, and for small movements here, I'm getting large movements in my negative D image, and I'm seeing large change. I'm getting my image to be very higher the height. So I'm seeing the magnification increase, and the image is appearing is upright. It's virtual, but it's on the wrong side of the lens. So I'm seeing this magnification. So this is D images. So this is becoming greater and greater, starting to be magnified, and my D image is starting to become a very big negative number, and that negative here makes it again be a positive number. So small movements in D object, the height, the magnification factor is increasing, and as I start to approach the focal length, here, this positive value, then what I start seeing is I start seeing the magnification approach infinity. This image is going far, essentially looking infinitely far away from the center of this lens, and it's looking infinitely large. And then an interesting thing happens when the object goes right at the focal point. Now what happens is when it's at that one particular point, there is no image. So I keep going towards infinity, and then at this, when the ratio of the object to the focal length is 1, I'm at the focal point with my object, there is no image. And then if I go a tiny bit past the focal point, or the focal length is slightly greater than focal point, and my distance to my object is slightly greater than my focal length, what happens immediately? The image it turns upside down. It's inverted. It becomes real, and it's a very large negative number, so as a magnification. And so I now I flip over to the other side, and I see, and now for small changes, additional changes in the object distance, there's big changes in the image distance, which is now positive. This magnification is now negative, and this is the only region where I see a real inverted image. And now as I keep going, and I get to finally to the radius of curvature, which is twice the focal length. My object is here and is a certain height. What I'll see my image also appear at that same a distance image, which is the same as that, and it'll be the same absolute value height, but it'll just be inverted. It'll be negative of that. So I come to this point where I have a magnification of -1. And then as I start to move my object farther and farther away, my image starts getting smaller and smaller. It's always still inverted, but it's getting smaller and smaller, and this distance traveled is getting smaller and smaller until eventually I get my object out at infinity. And as I'd expect, my object, as I put my object towards infinity, my image starts to approach, to be very, very small, and in the position of it starts to approach the focal length. And so I'm not going this part of the curve. And so in this whole thing, there's kind of three regions that happen. In the first region, here, for focal lengths greater than 0, my object's inside my focal length. I'm getting magnified, and it's not real. I get to my second kind of case where object right at the focal length, there is no image. Now object outside the focal length, and I'm now inverted on my image, and it has a large negative magnification. When I get to this case where the object's at twice the focal length, I have a magnification of -1, and then then the magnifications is continually always negative here. Negative magnification means image is inverted and the image is real. So, and this is the only in this all the scenarios, all the four cases for focal length less than 0, there never is a real image that ever exists, and only for focal lengths greater than 0, where the object is outside the focal length, do I get a real inverted image. Now let's consider what happens to a concave mirror. Again, the focal length is greater than 0. It's a very similar thing to a convergent lens, but in this case, recall that if the object's so this is the reflective side of the mirror. If the object's on this side, if I expect to see a real image, it will, because of reflection, the real image will appear on the same side. So positive distance is defined this way. So first case, again, we'll put the object right against the surface of the mirror. The image will appear also, the magnification of 1 right on the surface of the mirror. The height of the image is the same as the height of the object. So I'm at this point right here. Now I start to go into region 1 here again. The object's starting to move slowly away from the, in the positive direction, away from the surface of the mirror. The image is going to be the negative direction, and the image starts to get larger and larger. So I get a magnification which is starting to get larger than 1. And small changes in this distance of the object will make large changes in the distance of that the image appears to be. And the image distance is not positive, the image is upright, and the image is virtual, it's not real. And as I start to approach the object distance to be the focal length, now the image, this is starting to move very far away, and the image is getting very magnified, approaching infinity. And then same thing, if I go put the object right at the focal length, there is no image that appears. And if I have the image now the object slightly past the focal length, what I see is immediately the image appears inverted. It's on the actual positive side where I expect the image to be. It's real and it's huge. And so I'm at kind of a negative infinity for this magnification. And then as my my object starts to move a little farther out, my image is now starting to get closer. My distant image reduces, and my height of this image is reducing. Again, following this kind of linear relationship between distance of the image and height of this image. And then as I get to a case where I'm at the center of curvature of this concave mirror, which is this radius, this center of curvature, which is twice the focal length of this. Now I have my object and my image. The image is inverted, it's real, and it's the magnification is -1. They're the same absolute value as far as height, but the image is inverted relative to the object. And now if the object keeps moving, so I'm at this point right here. And so now if the object keeps moving away, the image starts to look smaller and smaller. It extends its state inverted, and as my object approaches infinity as far as distance away, the distance to the image starts to approach this focal length, and the height of this image starts to approach an absolute value of 0. One last thought about devices like maybe a telescope, which may contain a convergent lens, and its required length and how you might adjust it. If an object is a long way away from this device, and then the center of this lens, then the image will appear slightly outside the focal length. So I would have this telescope, this object would be in a short setting. But if then I switch to look at some object which is closer to the lens, I would need to make the telescope longer, because my image is now appearing at a distance farther away from the center of the lens.